Okay, so the first thing that people came up with were these percentage errors, right? So the idea is, okay, well, let's just divide by the actual, right? So we have a percentage error where we have on top the error, actual minus the forecast, and we divide by the actual, and now we calculate the mean and the absolute value over that, which gives us the mean absolute percentage error, which is this thing here. And yeah, the MAPE has been very standard measure. It still is a standard measure, but it's not very good. And we're going to talk about that now, why that is. So the first problem is it cannot be used if y is 0, because then we divide here by 0. And it is quite distorted if the yt is small. And it was originally used for inventory count data, so these numbers were never small or 0. So that's why that was not so much of a problem. It is also not symmetric, so if you exchange the prediction and the true value, the result is not the same. So if I say yt is 50 and my prediction is 60, it's not the same as if your true value is 60 and your prediction is 50. And another big problem that it is minimized by a statistical quantity that is called the -1 median of the forecast distribution. And what that means is the following. So here I have just some simulated log normal data. They are IID. So your ideal forecast distribution is just the distribution that I plot here. And now the blue line is the forecast that you get that minimizes MSE. So if you take MSE for evaluation, the blue line is the best forecast. If you take MAE for evaluation, the green line is the best forecast. And if you use MAPE for evaluation, the red line is the best forecast. So now, do you think that this red line, that this red point here is a good forecast? Because it seems to heavily under forecast, right? So, but that's what you get as the optimal forecast when you minimize MAPE. Okay. Yeah. Another problem of the MAPE is that, 50% of error can have very different consequences. So the MAPE tends to focus more on the series with small values as they tend to have larger errors. So here I give you an example. On this series down here, which is some sales I've made up that are between 0 and 3, so just some slow moving item. And now imagine the next value here is a 1, but you predicted a 0. That's 100% forecast error, right? Or let's say the next value was a 1, but we predicted a 2. That's 100% forecast error. And now compare this with making 100% error here. So basically the next value, instead of 320, we predict 600 up here, right? Obviously very different situation, but for the MAPE it looks the same. It's always 100% error. Yeah, so that's obviously not good if you then start just averaging over these very different things. And obviously, yeah, the MAPE will usually be dominated by these ones here, which later for your application are probably the ones that you are not too worried about. You're much more worried about catching something like this and not catching something like this. Yeah. Okay, well, so the next measure that was proposed is the sMAPE, the symmetric MAPE that tries to fix some of these problems. And the way it does it is that it in the denominator, well, here in the denominator, instead of just dividing by yt, you divide by the average of yt and the forecast. So it achieves the symmetry from before, so you now can exchange yt and yt hat and get the same value, but it breaks another symmetry. Over prediction is now penalized less than under prediction. That can be easily seen because you're dividing now by the forecast. So if this forecast is smaller, the forecast gets, the overall error gets bigger. Okay. So yeah, sMAPE is called symmetric, but it has one symmetry but breaks the other. It also has still problems with zeros, right? I mean, if both your actual and your forecast are 0, you're still dividing by 0. Yeah, and another problem is that if there is a 0 in the data, but we don't predict an actual 0, the sMAPE is maximal, right? So let's say yt is 0, so that goes away. So we now have just yt hat divided by yt hat, and if this is 0, then it's kind of undefined, or we would probably then define it to be 0. But if you predict 0.0001, then this term here becomes 1, and your overall error is 200, which is the maximal error that the sMAPE can be. Yeah, so not great, and this has large implications for intermittent data. So if you use the sMAPE to evaluate intermittent forecasts, then your main concern will be to predict zeros as exact zeros. That's what your methods will then hone in to get zeros exactly right. Yeah, but a big advantage of the sMAPE and why it's still used, and some people really like using it, is it's bounded by 200 no matter what. Okay, now we have this modified sMAPE. It's actually people now, this is one example, but there are similar solutions where people say, well, okay, if we don't want to divide by 0 and we don't want this denominator to be too small, why don't we just add an epsilon to it? Right? And then, yeah. And then we can also take like the maximum of so if this part gets too small, we just choose some constant value here, right? So that it doesn't get distorted too much. Yeah, I mean, it's an ad hoc solutions for this problem with zeros and small values. It does work. But the problem is it does make the evaluation skewed so that it's not minimized by any meaningful summary statistic of the forecast distribution, right? So you're now not optimizing anymore towards the mean of the forecast distribution or the median. You're optimizing who knows what. So statisticians don't like these ad hoc fixes, but in machine learning, people do that. Another measure, just as an example of something more recent that people have come up with that I wanted to show you, is this mean arctangent absolute percentage error. The idea here is basically that we have this arctangent in the MAPE, so otherwise it's pretty much a MAPE. Yeah, so that was proposed in 2016, so yeah, relatively recently. And here the authors argue that it is more interpretable than the MAPE. And another advantage is that it is p-half instead of infinite when yt is 0. But it has the same problem as sMAPE, that if yt is 0, it is always maximal no matter what yt hat is. That's because if yt is 0, you have here 0, here 0, here some number, doesn't matter what, because the whole thing is infinite, and then the arctangents of infinity is then this p-half. Yeah, so therefore it is also not good for intermittent data, same as sMAPE. Okay, the next one are relative errors and error measures. So the idea is we now use a benchmark method B, which is usually the naive forecast. Sometimes people use seasonal naive, sometimes people use ARIMA or whatever. And now you can do relative errors. So you're now dividing by the error of this benchmark method, right? So that's the error of your method up here, and down here is the error of the benchmark. And now you can just calculate the mean absolute error over this, which gives you the mean relative absolute error, MRI, which would be defined like this. Yeah, it has the same problems as before. If the true values are 0 and predictions from the benchmarks are 0, etc. So that's why then people said, let's do relative error measures instead. So instead of doing at first the division and then the sum, why don't we first do the sum and then the division? So let's get the mean absolute error, which is the mean over all the absolute errors, and then divide that by the mean absolute error of this benchmark. And we'll get back that in a moment, but I mean, this has, that obviously works if over what I compute this measure is more than just one value, right? So if I have many predictions on, and now obviously we are summing before we are dividing. So that means we now need a certain amount of errors that are on the same scale over which we can calculate this sum. And then it works. But if you have only one forecast, or you try to average over different things, then it doesn't work.